Hey everybody, I'm Kartik Paigwar. I'm a research assistant at Indian Institute of Science. Today I'm going to present our work, Robust Quadrupedal Locomotion on Slope Terrains, a linear policy approach. The domain of quadrupedal locomotion has reached maturity today with quite a few research labs and companies commercializing their quadrupeds. Trotting on slope terrain has successfully demonstrated by several groups in the past. However, their approaches rely on expensive series elastic or costly direct drive actuators. Also, they rely on sophisticated sensors. On the other hand, there is an active community developing open source low cost quadruped robot. Some of these robots do not possess BLDC motors for accurate torque control and have limited sensor modalities. In addition to that, they lack expensive computational resources required to run advanced control laws like MPC and deep neural networks. Developing a robust controller for such budget-friendly robots with limited capabilities is quite cumbersome. Therefore, the goal of our work is to develop a minimum possible control framework that can be deployed in medium-sized, low-cost quadruped robots in order to realize stable locomotion behaviors on challenging terrain. While the long-term goal of our work is to automate this process for a broad set of quadruped robots without much need for domain expertise. Locomotion on slopes requires different strategies than on flat ground. In particular, two distinct strategies are well known in biomechanics, namely telescopic strut and lever mechanism. In these strategies, the posture as well as the swing leg trajectories need to be adapted on the underlying terrain. Inspired by these strategies, we propose a simple control framework for budget-friendly quadruped robots such as Stoch 2 in order to dynamically trot on arbitrary slopes. Here is our control framework. It consists of a slope estimator which calculates the orientation of the underlying terrain by fusing inertial measurements and kinematic data from the joint encoders. The estimated support plane orientation along with the history of torso orientation is given as an input to our trajectory planner, which is nothing but a linear policy that outputs a set of transformations for semi-elliptical foot trajectories. These transformations include variation of step length, steering of trajectory, and shifting these trajectories along x, y, and z axes of the local frame of reference. We learned this linear policy using augmented random search technique. Our linear policy is a single matrix of 20 cross 11 dimension, which can be implemented on a cheap embedded microcontroller and has a very low inference time. The end-foot trajectories are phase-shifted according to the trot gate controller, and corresponding desired joint angles are then tracked by the PD control law, resulting in stable walking. In our training process, instead of random initialization of the policy matrix, we use an initial policy matrix learned using a set of hand-tuned actions derived from telescopic strategy, as we discussed before. This has marginally improved the sample efficiency of ARS algorithm. We randomize the terrain during the training in order to generalize across multiple elevation and orientation. We incorporate the robustness of the policy by using two schemes. First, by domain randomization. Second, by applying random external forces on the robot base. We validate our policy across arbitrary slopes. It is even able to climb staircase unseen in the training, due to the fact that the staircase with low risers resembles an elevated terrain. It is also worth noting that our policy is able to generalize on downslopes while it is only trained for uphill. This clearly explains that there exists a simple linear relations that maps the elevation of the underlying support plane to the transformations of the foot trajectories. We verified the scalability of our approach by deploying the controller on robots like Haiku and Lycago, which have different physical properties as compared to Stock 2. Experiment shows that the train policy could generalize across arbitrary slopes out of the box without the need of any form of manual tuning. Hereby, I conclude by thanking all my fellow collaborators for making this work possible despite the pandemic through their valuable remote contributions from different parts of the country. In future, we would like to validate our controller in hardware and further extend it for multitude of quadruped robots. Thanks for listening, and I would be happy to answer if you have any questions.